Welcome back to Mechanical Engineering Made Simple. If I asked you to mix a huge industrial vat, you might think, okay, I'll grab a big propeller and just turn it on.
Yeah, how hard can it be?
Exactly. But today, we are diving into a world where that simple act becomes a really critical precision engineering challenge.
It absolutely
We're
is.
talking industrial mixing. And this isn't just simple stirring. It's a field that demands a sophisticated balance of everything.
Yeah.
Optimizing complex process needs, mastering intense fluid dynamics, and ensuring total mechanical reliability for equipment that might have to run nonstop for 20 years.
It's the ultimate intersection of process chemistry and heavy-duty structural mechanics. Our mission in this deep dive is pretty straightforward.
Yep.
We're going to distill the critical, non-negotiable role the mixing equipment supplier plays. And we'll lay out the engineering factors, from the basic parameters like sizing, all the way to managing severe dynamic mechanical loads that really dictate whether a system succeeds or fails. And we're talking about massive applications, sometimes in tanks holding millions of liters.
So we're going way beyond just stirring. We're getting into the structural integrity that makes it all possible.
That's the plan.
Okay, let's unpack this then. The sources really emphasize that a successful, reliable mixing setup begins, well, long before the first piece of steel is even cut. It requires an intensely close partnership, and this is the key, a complete information exchange between the purchaser and the supplier. So if a buyer has proprietary secrets, why is sharing that process information so fundamentally crucial?
Because the final mixing configuration is sensitive to absolutely everything. The supplier has to understand the environment, the constraints, and maybe most importantly, the priorities.
What do you mean by priorities?
Well, things like the position of the impeller relative to the liquid level, the tank geometry, even where you place the baffles. All of it dictates the flow pattern and where the shear forces are distributed. If the supplier is working blind, the machine they provide it's essentially a guess, a very expensive guess.
I noticed in the sources they talked a lot about conflicting needs. What kind of engineering conflict comes up when you're trying to optimize a process like this?
A classic example is the trade-off between high shear and high flow. It's a constant battle.
Okay.
You might need really high shear energy to accomplish, say, a fine dispersion like creating a perfect emulsion where the droplets are microscopic. But to make sure that dispersed material actually reaches every corner of the tank, you need high bulk flow for blending or solid suspension.
So you're asking the mixer to do two different things at once.
Exactly. Two things that pull against each other mechanically. If the purchaser doesn't specify which task is the absolute most important, the process yield severs. The engineer has to make a calculated compromise.
That makes a lot of sense. So when you're submitting a request for proposal, an RFP, you can't just say, I need a mixer for a 10,000-liter tank. You have to get into serious detail.
Oh, it has to be comprehensive. They need a list of all materials, liquids, solids, gases, including both the nominal and the peak amounts. You have to define the operational mode. Is it batch or is it continuous flow?
And what about the process itself?
Here's the critical insight. You have to identify which step in the overall manufacturing process is the rate controlling step. That tells the engineer where they can, afford to save power and where they absolutely must allocate maximum energy.
And for applications with solids, like solid suspension, the detail gets almost microscopic. Are we really talking about specifying individual particle sizes and densities? That sounds like overkill.
It's not overkill at all. It's pure physics. You absolutely have to specify particle size and density and precisely what level of suspension you require.
What are the different levels?
Well, do you just need off-bottom suspension, which is just enough energy to keep the solids from settling and building up? Or do you need full suspension, where those particles are uniformly distributed throughout the entire liquid volume?
And the power difference is significant.
The difference in required power between those two states can be monumental. It's huge.
Wait a second. Something in the sources really jumped out at me. It said that the way they pour the raw feed into the tank actually changes the dynamic loads on the mixing structure. That's not just a process variable, that's a structural one.
That's where it gets really interesting. That's where fluid dynamics connects right back to the mechanical design. The purchaser has to specify the characteristics of the inlet feed, the velocity or the flow rate.
Why?
If you have a powerful stream aimed directly at the impeller, that stream introduces substantial calculable forces. The equipment supplier can't just focus on the loads generated by the impeller itself. They have to account for those external dynamic forces from the process stream.
Which means what for the hardware?
It means designing a thicker shaft and a more robust speed reducer. It changes the entire mechanical design from the ground up.
Wow. Okay. So once all that process detail is locked down, the focus shifts to the raw physics of sizing the actual machine.
Exactly. The foundational steps are pretty standard. Customer specifies the process goal, the tank geometry like its diameter, and the volume. Then the supplier uses their own proprietary correlations and modeling to calculate the required power, select the best impeller type, determine its diameter, and then establish a safe operating speed.
But the sources make it very clear this isn't a linear process. Let's talk about the D/T ratio, the ratio of the impeller diameter to the tank diameter. They call this a very strong function of power. Why does that specific ratio have such a massive impact on energy needs?
This is where understanding fluid circulation becomes absolutely vital. For an axial flow impeller that's designed to suspend solids, there's usually an ideal ratio. It's often around 0.35. And at that ratio, it creates a perfect, predictable circulation loop, efficiently lifting material off the bottom and sending it up to the surface. But if you increase that impeller diameter, pushing the ratio up to, say, 0.5,
The power goes up a little bit.
it doesn't just creep up, it explodes. You might suddenly need 1.6 times the optimum power.
Why such a massive exponential jump? That seems counterintuitive.
Because the larger impeller physically starts to cripple its own axial circulation loop. Instead of efficiently pumping fluid around the tank, the impeller is now pushing fluid against itself and against the tank wall. It severely disrupts the very flow pattern the system needs to live.
I see.
So the efficiency just plummets, and you have to dump massive amounts of extra energy just to force the fluid to move. It's a self-inflicted wound caused by going just slightly oversized.
That inefficiency and mechanical stress, that brings us directly to the next non-negotiable factor, avoiding the critical speed, or NCRIT.
Exactly. NCRIT is the natural frequency of the entire rotating system.
Yeah.
The shaft, the impeller, any attached components. You can think of it like a perfectly tuned tuning fork.
Okay.
If the operating speed, N, hits or even gets close to that natural frequency, the whole shaft system enters a state of uncontrollable, undamped vibration. It's called resonance.
It's like driving on the highway and hitting that one specific speed, say 65 miles per hour, where your entire car just starts shaking violently.
That is the perfect analogy. Except in this industrial case, the shaking doesn't just annoy you, it breaks the whole machine.
Catastrophically. Yeah.
That vibration causes rapid mechanical fatigue on the shaft, on the seals, on the gearbox. It leads to failure. So to protect the system, the standard engineering design rule is mandatory.
And what's the rule?
The operating speed, N, must be kept 20% away from the critical speed, NC. So the operating speed must be less than 0.8 times NC, or it has to be greater than 1.2 times NC. You just can't be in that middle zone. And this applies to the first, and often the second, natural frequencies of the system.
And this critical speed management ties directly into the big economic equation, right? Capital cost versus operating cost.
It absolutely does.
Yeah.
A larger impeller diameter, for example, typically reduces long-term operating costs because it uses less power. It moves more fluid volume per rotation. But
There's always a but.
there's always a but. That larger impeller creates much higher torque requirements. Higher torque means you need a larger, heavier speed reducer, the gearbox, and a significantly thicker, sticker shaft to keep that operating speed far away from NCRIT.
So the engineer's real challenge is finding that precise sweet spot.
It's an optimization problem you have to solve before the machine even starts running.
Okay, let's shift gears a bit and talk about the hardware catalog. The variety of mixing equipment is huge, but we can kind of categorize it by what the impeller is engineered to do. You have high flow, low energy impellers versus high shear, high intensity ones.
Right. The high flow, low head impellers, like a high efficiency flow impeller, are designed for maximum volume movement. Their efficiency is defined by something called the power number, or NP.
And what does that tell you?
It tells you how much power a given impeller needs to generate flow. A low NP, typically around 0.3, means you are highly efficient. You move a massive volume of liquid for very little energy input. These are your workhorses for, mild blending or basic suspension.
And on the other end of the spectrum, you have the specialized high shear impellers.
Yeah, these are built for specific tasks like fine dispersion, high-intensity blending, or incorporating really difficult powders. They run at very high speeds and typically have a power number closer to 0.45. They basically sacrifice bulk flow for intense local turbulence and extreme energy dissipation.
Looking at the physical designs, we can start small with portable mixers. These are usually running from a quarter horsepower up to maybe 3 horsepower.
Right, and they're often just clamp-mounted to thin-walled tanks and use pretty basic axial flow impellers.
Then you step up to top-entering mixers.
These use more fixed mounting structures, flange or pedestal mounts, and might go up to 10 or 15 horsepower. They have robust mounting to stabilize the shaft and a much better mechanical seal system, which is crucial for closed vessels.
And then you get to the heavy-duty segment, the massive turbine mixers.
Now you're talking. This is a broad class that covers the most robust designs, running from 1 horsepower all the way up to 1,000 horsepower or even larger. You'll see these in almost every massive chemical processing application imaginable.
We can't overlook the true specialty mixers, though, where the fluid properties themselves completely dictate the machine design. Like for high viscosity applications, fluids over 100,000 centipoise.
Right, for those of us who don't have a viscometer handy.
I was just about to ask, what is 100,000 centipoise like in the real world?
That's like trying to mix something thicker than peanut butter, or cold honey, or heavy grease. You are no longer generating bulk circulation flow. You are physically dragging the material through what's called plastic flow.
So you need a totally different strategy.
A completely different strategy. You shift to a close clearance impeller. The impeller diameter has to be 85 to 95% of the tank diameter. You see styles like helical ribbon or anchor impellers.
And the mechanics of that.
The key mechanical outcome is extremely low operating speed, but enormous torque to overcome that viscous drag.
And conversely, high shear mixers are the other extreme. They use very small impellers, sometimes only 10 to 20% of the tank diameter, but they spin at incredible speeds, up to 3,600 RPM.
The visual is really essential here for the listener. Picture a disc impeller with teeth all around the edge, or even more complex, a rotor stator design. The rotor spins inside a stationary cylinder that has slots in it.
And the fluid.
The fluid is physically forced through that narrow gap, creating maximum mechanical and localized hydraulic shear. It literally rips particles apart or forces immiscible liquids to combine.
So what this all means for the components is that whether it's a tiny portable unit or a massive turbine, the core mechanical parts, the motor, speed reducer, seal, shaft, and impellers, they all have to be engineered specifically to withstand those calculated severe dynamic loads. That shaft design has to be rigid first, strong second.
Absolutely. And the supplier's job extends well past just the initial design. It involves rigorous verification and testing. Most pre-purchase customer sample testing is done on a relatively small scale, maybe in a 0.45 meter diameter tank.
So a lab scale test.
Exactly. And the primary engineering challenge then becomes scale up, moving from that small sample to a massive industrial reactor.
And the sources warn that you can't just scale up the size and use the same materials, right? The physical properties change with scale, particularly viscosity reduction.
Precisely. If you use the same viscosity material on the small scale and the full scale, the flow regime might be, say, transitional or even laminar in the sample tank. But at full scale, it's highly turbulent.
So the test isn't valid.
You have to model that viscosity reduction correctly to make sure the process achieves comparable flow conditions at full production capacity. If you don't, the full-scale unit might underperform drastically.
Fortunately, engineers have some incredibly advanced diagnostic tools now to peek inside the flow without actually touching it. We see tools like laser Doppler velocimetry, or LDV, and particle image velocimetry, PIV.
These are non-intrusive tools. They're used specifically to measure the velocity and the entire flow field inside the vessel. This is crucial for optimizing impeller placement and, critically, for identifying undesirable low-velocity regions.
Which often pop up in surprisingly key areas, right? Like near the top surface where you're adding ingredients, or in those little dead spots tucked right underneath a big impeller at the bottom of the tank.
Identifying and eliminating those dead spots is key. It's how you avoid inconsistent blending, unwanted heat buildup, or localized reactions.
And then there's computational fluid dynamics, CFD.
Right. And this modeling tool is becoming excellent and increasingly cost-effective. We can use CFD to model really complex flow patterns, maybe visualize how multiple up-pumping impellers interact with each other, and it can calculate the power number with an accuracy of just a few %, which validates the design before you even fabricate any steel.
But all that process optimization is, well, it's meaningless if the machine tears itself apart after 6 months. Let's get back to mechanical reliability, which hinges entirely on knowing the fluid loads.
The shaft is under constant chaotic abuse. The dynamic loads applied are torque, bending, and thrust. What's truly astounding is the randomness of the fluid flow. even when it's under steady operation.
How random are we talking?
The blade loading on the impeller can vary dramatically. We're talking sometimes by as much as plus or minus 40% to plus or minus 100%, depending on where local turbulence is hitting the blade at any given millisecond.
Wait, plus or minus 100%. That means the load is constantly oscillating from 0 to double the average load hundreds of times a minute.
Exactly. The entire mixing system has to be engineered not just for the average load, but for that extreme, chaotic fatigue cycling.
Which is why we come back to the critical speed rule.
That's why we come back to it. Stay 20% away from the first and second natural frequencies, period. Your operating speed, N, cannot be greater than or equal to 0.8 times NC, and it can't be less than or equal to 1.2 times NC. Stay out of that band.
And finally, let's address the tank support, which is often overlooked. The sources are so insistent on this. The mounting structure must be stiff, not just strong.
Yes. Strength ensures it won't collapse, but stiffness ensures it won't move. A structure designed only for strength might experience noticeable deflection or movement under a dynamic load, and that flexibility actually reduces the overall system's natural frequency.
And if you have poor mounting, say with those portable mixer clamps on a thin-walled vessel,
Right.
that non-rigid support effectively lowers the calculated critical speed of the shaft. The actual critical speed could be much lower than the engineer calculated.
Potentially dropping the operating speed right back into that dangerous resonance zone. And that leads to dangerous vibration and failure. It's a classic failure mode that starts at the foundation.
So if we were to summarize this entire deep dive.
To summarize this entire process, effective industrial mixing is fundamentally an optimization problem. It requires meticulously balancing the desired process yield your product outcome against the long-term operating costs, which are all about power consumption, and against the essential, non-negotiable mechanical integrity, which is managed through torque capacity and critical speed control. It's a three-way balancing act.
And thinking about that long-term integrity, let's leave you with one final provocative thought, this one based on material selection mentioned in the sources. The actual metallurgy matters a lot for decade-long reliability. Take 317L stainless steel.
Okay.
It's often chosen specifically for its resistance to chloride corrosion. Now, the engineering specifications for 317L allow a molybdenum content range of 3 to 4%.
Right. Due to market realities and cost pressures today, new batches of that steel often contain only 3 to 3.25% molybdenum, the absolute lower end of that range, which is technically still compliant with the specification.
Whereas 20 years ago, a mixer built of 317L would have averaged closer to, say, 3.5% molybdenum. That subtle difference in composition, while still meeting the spec, could dramatically shorten the lifespan of the equipment in a corrosive, high chloride environment compared to older material carrying the exact same designation.
So even if the paperwork looks identical.
Exactly. It shows how subtle market pressures can reduce long-term reliability even when technical specs are met. You have to understand what you're buying today to protect your investment tomorrow. And if you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use. A family that solves together stays together.